Before we get started, I have a quick favor. I've been self-funding the Finding Genius podcast for 5 years now. I've done over 3,000 episodes. And as you can see on YouTube, we're up over 1 million views on the channel, which is fantastic. The next thing I really want to push on is to get up to 10,000 subscribers. Because once we do, we'll be able to put a donate button and we'll be able to solicit donations to help keep the podcast running and to also get the Finding Genius Foundation moving along. We have a big project studying anxiety, depression, and PTSD and working on a product to help people overcome these problems because I've seen them explode recently after the last 2 years of the whole virus situation. So if you would, please subscribe to the podcast. That would help us tremendously. Give us a thumbs up and check in the description for Buy Me a Coffee. It's about $5. If you could buy me a coffee, I'd really appreciate it. It would help keep the channel going, and I love coffee. Thank you.
Forget frequently asked questions.
Common sense, common knowledge, or Google.
How about advice from a real genius? 95% of people in any profession are good enough to be qualified and licensed. 5%
Go above and beyond.
they become very good at what they do, but only
0.1%.
are real geniuses. Richard Jacobs has made it his life's mission to find them for you. He hunts down and interviews geniuses in every field: sleep science, cancer, stem cells, ketogenic diets, and more. Here come the geniuses. This is the Finding Genius Podcast
With Richard Jacobs.
Hello, this is Richard Jacobs with the Finding Genius podcast. My guest today is Matt Greenhouse. He's an ISIM project scientist at NASA, and we'll define what the acronym means. But we're going to be talking about the James Webb Space Telescope. So welcome, Matt. Thanks for coming.
Sure. Thanks for having me.
Yeah, tell me a bit about your background and your role at NASA, and then we'll start focusing in on the telescope.
Well, I'm infrared astronomer, and I joined NASA in 1996. I was at the Smithsonian in Washington before that. And I started on the Webb Space Telescope project in 1997 through launch. And my role was I'm the scientist responsible for the science instrument payload on the observatory.
Oh, all right. So it's a whole array. I guess it's a whole array of instrumentation on the James Webb. So what are some of the elements on there, and what do the elements do? What are they looking for and analyzing?
Yep. 4 science instruments that extract the physics information from the starlight that we're observing, and then 9 other systems that support these instruments and enable them to work in space. The instruments support imagery and spectroscopy across a broad spectrum extending from the red end of the visible light that we can see with our eyes, 0.6 microns, out into the mid-infrared light that we can't see with our eyes, out to about 28 microns wavelength or so. And then these science instruments also support something called coronagraphy, which allows them to observe exoplanets that are, very close to their very bright host stars. And so it requires special optics to observe them. And the Webb is doing a lot of work on exoplanets.
Okay. Well, I'm sure the James Webb's time and eye is booked for quite a while. So what are some of the time that's booked by you? Let's say if you were the one that in particular that did it. What in regards to exoplanets, what's going to be looked at and where?
Well, the way we run these observatories, once a year, a call for proposals is sent out to the worldwide astronomical, and anyone in the world can answer that and write a proposal to observe something with the Webb telescope. And as you can imagine, we get many thousands of such proposals every year. And those proposals are reviewed they're subject to something called peer review. They're reviewed by peer scientists in a double-blind fashion. And through that review, some of the proposals are accepted and approved, and those projects are executed. So on each one of these cycles, we select a year's worth of observing, and then we repeat this. And so we're just finishing up selection of cycle 4 of this process. And then, so when we complete the process every year, we have a year's worth of observing projects queued up to execute.
Okay. So yeah, in regards to, again, exoplanets, what are some of the things that are going to be looked at?
Well, we're studying the atmospheres of exoplanets because we have learned how to search for potential life on exoplanets using a spectroscopic technique that JWST can do called transit spectroscopy. You know, when I was a graduate student, there were no exoplanets known. There were no planets known outside the solar system. Today, we have identified more than 5,000, with the implication that all stars have exoplanets, have planets, and that in turn implies that there are billions of habitable worlds in our galaxy alone. We don't know that they're inhabited, but we know that they're there, and we have learned how to search for life on them by studying the chemical of their atmospheres using spectroscopy, which is a technique that allows us to identify light that is emitted by individual atoms and molecules in the atmosphere of the planet, light that is emitted and absorbed by atoms and molecules in the atmosphere. We can identify that chemistry, and we're looking for chemistry that would be unexpected absent biological processes. And so this is the way that the Webb telescope will contribute to the search for life, which is a major science objective of NASA. Webb will be primarily working on exoplanets that are somewhat larger than the Earth. The Webb can detect water vapor on a planet that is about 3 times the size of the Earth. And when we look for extraterrestrial life, you know, we focus on water not because the alien life might get thirsty and need something to drink, but rather for the organic chemistry of life to occur on a planetary scale. One needs a liquid solvent available on a planetary scale, and water is we're most familiar with. So the Webb has observed lots of exoplanets to date and has found many with atmospheres, and they have identified lots of chemistry in those atmospheres. And so the work is very exciting and is just getting started.
Well, how do you know a world's habitable just because it has liquid water on it?
Well, it takes more than liquid water to be habitable, but water is a necessary condition, but not sufficient. We need to see what are called biomarkers or bioindicators, chemical species, molecules that would not be present in an abiotic. And so that's what we're looking for. It's a tough job. It'll take a while, and one has to observe, you know, lots and lots of such molecules, not just one. But that's the technique that we're following, and so stay tuned. It's going to be very exciting.
Well, what are the criteria? So water, what else?
Well, we need chemical species that cannot be produced by any abiotic process. So, you know, one thing that was observed recently, dimethyl sulfide, that's a compound that's produced only by phytoplankton on the Earth, but it may or may not be a valid bioindicator, you know, So we have to build up a library, if you will, of potential bioindicators to make the case for life in a particular atmosphere that observes enough of them that the chemistry cannot be explained any other way.
Okay. When you talk about exoplanets, is it worthwhile looking at planets in our solar system, or, you know, like where distance-wise and location-wise, you know, in the universe would be good places to look for them and characterize them?
Well, as I said, all stars have planets, and the closer they are, the easier it is to observe them and characterize them. So, you know, we're working hard on planets that are like within 10 parsecs or so of the Earth. Now, the planets of our solar system, you know, form a template from which we interpret other worlds. The planets of our solar system are the ones we're familiar with. And we've put special non-sidereal tracking into the Webb telescope so that it can observe the outer planets of our solar system and something called the Kuiper Belt objects in our solar system. These are chunks of rock and ice that are still orbit the sun in the outer solar system and are material that is just left over from the formation of our solar system. And so the Webb is working hard to study that material and study the atmosphere of the outer planet to understand how they work, and also to help us interpret what we see in solar system.
Okay. But again, where is there in the universe like a sweet spot? Why would certain places be more amenable than others? For instance, are they near a bloody? Are there a lot of interstellar gases?
The sweet spot is the exoplanets are orbiting stars, so we want to look where the stars are. That's largely in the galactic plane, and we don't want it to be too far away, so we try and work within 10 parsecs of the Earth. And just for that volume or sweet spot, as you call it, there are innumerable stars and exoplanet candidates. We have prior missions that have flown to search for exoplanets. So there are extensive target lists available for JWST from those precursors.
Are there any ones that for some reason would be faster to look at or easier to look at? Like, in the moving of the James Webb, would it be better to look at a planetary system that has a bunch of habitable planets in it? Or does it matter if it rasters back and forth looking, or if it moves left, moves right, up and down, and looks all over the place and changes its focus? Like, what would be the most efficient use of the James Webb, if there is such a thing?
Well, it doesn't work quite like that. The telescope is precise if we're observing an exoplanet. The telescope is precisely pointed at that exoplanet to within a few millionths of a degree. And these exoplanets are very, very faint. So the telescope has to stare at the exoplanet for many, many, many hours to develop a signal that exceeds the noise by a sufficient amount. And so the observatory is not so much searching for exoplanets, but characterizing exoplanets that have been identified by other missions.
Okay. What makes a planet a good potential candidate to look at upon first observation?
Well, if it has an atmosphere, that makes it particularly exciting. So the first step in studying an exoplanet is decide, is it a rocky planet? Is it a gas giant? Does it have an atmosphere? Those are the sort of broad brushstrokes. And if we find an exoplanet that is at a distance from its star such that liquid water might exist on its surface, and it's a rocky surface with an atmosphere, that planet would be of great interest and would probably be studied pretty hard.
Okay. Like you said, what is the total current estimate of habitable planets right now in the universe? Is there any way to even get a feeling?
Billions in our own galaxy.
Oh, okay. Okay, there's tons and tons and tons and tons. Even within our own galaxy, again, are there clusters of them with this, thousands in a very narrow area, again, without a lot of potential interference, without a lot of other activity that would obfuscate, viewing, like a nice nursery of them or something that you can find?
The planets are where the stars are. And so it's just the distribution of stars. I mean, there are planets that are unbound, and there are some who feel that there are more unbound planets than bound ones. The unbound planets are incredibly difficult to see or find because they're cold. They're not in orbit about anything. They're like chunks of debris. But yeah, wherever the stars are, that's where the planets are. The stars are primarily.
I've never thought about that, an unbound planet. Like Pluto, well, it's not a planet anymore, legend has it, but yeah, we'll just say Pluto or Uranus or something. Let's say Uranus. It's so far from the sun. Like what is considered bound? How far can you be from a star to be considered unbound?
Well, unbound means you're not in orbit about the star. And
how big can an orbit be, theoretically?
Well, it depends on how big the star is. When the star forms, let's talk about how stars form for it. The spaces between stars in our galaxy and others, the so-called interstellar space, it's not a cold, empty vacuum filled with lots of stuff. Atoms, molecules, giant clouds of molecular gas and dust. And this molecular gas is primarily molecular hydrogen. In these giant clouds of gas, collapse onto themselves with self-gravity. And as the cloud collapses onto itself, the temperature inside the cloud begins to rise. It's much like when you fill your bicycle tire at the gas station. The tire gets a little bit warm when it's fully compressed. In the cores of these clouds, the same thing happens, only there it gets really, really, really warm to the point where nuclear fusion can occur. And then the star is born. And when the star is born, it's typically surrounded by a disk of material, a circumstellar disk that you could think of as material left over from the star formation. Those circumstellar disks are of tremendous scientific interest because they are the places where planetary systems like our own form. And when planets form in that disk, it can be a pretty violent process. There are a lot of collisions and things that occur among bodies that are condensing in this circumstellar disk. And, sometimes the kids could get lost. And so there are apparently lots and lots of unbound planets simply drifting from interstellar space. They're nearly impossible to see because they're cold and they don't emit light. But sometimes we can tell they're there by when they occult light from a star that we can see.
Well, what is it like? I mean, so have we flown by any, unbound planets? Has any of our satellites in there?
The only thing that humans have made that have left the solar system are the Voyager spacecraft. And they're just outside the solar system. But, because of the Voyager spacecraft are legitimately an interstellar species. We have built something and sent it into interstellar space, and we're still talking to it today.
Oh, is Voyager? I thought, the furthest one, what is Voyager 1?
Yep.
But has contact been lost, or is it still...
No, you're still talking to the Voyager.
All right, and there's another thing to explore. What information is coming from them?
Well, we're learning about the edge of the solar system and, how the atmosphere of the sun extends out past the solar system. And, the various shock fronts and so forth exist there. So, it's helping us understand that environment. Their science mission is long since, been over. No one ever imagined that they would actually last this long. But they have, and we're still in communication with them.
Oh, right. Well, Voyager 1 was what, like in the 70s it went out, or when did it go out?
Yeah, it's been a long time. So it's remarkable.
So how far is it? I don't know how would you express it, but what's like an object that's the further, I guess, again, let's say Pluto. How far is it past Pluto?
It's outside the solar system, so it's farther than Pluto, well outside the solar system. I don't happen.
What would it be called, like interstellar space that it's in?
Exactly. They're both in interstellar space.
Huh. So it's going through a vast nothingness, I guess, essentially, right?
Yeah.
Weird. Is any of the data that comes back from them, I guess it's saying the conditions, there's less and less matter out there, but is there anything it's seeing out there? I mean, is there any visuals, or is it all just, just
image data? But, I'm not on Voyager, so I'm not really able to talk to you in much detail about them.
Yeah, just as a side question, is there anyone at NASA that is still...
JPL still runs the Voyager program.
Huh, very interesting. Okay. Well, I guess let's return to these unbound planets. I don't know why they just seem like very mysterious, fascinating things. That's why I've asked you about them a couple of times. But any quick rundown, like what is known about them? Like how have we identified where like any of them are?
There's some that are known from occultation studies, but nothing else is really known.
Has anyone pointed a telescope at them?
Well, there's nothing to see from the planet themselves. You can see, by occultation, if you're looking at a star, imagine one of the unbound planets drift through your line of sight to the star would be occulted. And with that, you could perhaps measure the size of the planet, but very little is known about.
Are they just like gigantic asteroids?
Yeah, they're like planet-sized pieces of rock and ice that are drifting through interstellar space.
Sheesh. Has it ever been observed, the unbinding of a planet-sized body from a star system?
We haven't been able to observe planet takes place over planet formation takes place over a very long period of time, 10 to the 8 or so. So we haven't been able to sit back and watch that process, occurring. We can see it in different stages. We see planets that have formed, but we can't sit back and watch it like a...
Okay. Well, I guess so back to the James Webb, what are some of the observations that it's made that you're, personally interested in that intersect with your work that we can discuss?
Well, I am like most of astronomy. I'm very excited about the exoplanet work and looking forward to seeing what materializes from that. The Webb telescope has shown us the early universe first time because it's an infrared telescope and only an infrared telescope can see the early universe because the light that's emitted at that time is all been red shifted into infrared. So you have to have an infrared telescope to observe it today. And so, the Webb is showing us the early universe for the first time. We're seeing lots of new phenomena. And the Webb is also showing us the infrared universe in high definition for the first time. The Webb is literally giving humanity first high definition of the infrared universe. And a lot of the science impact of the Webb comes from its ability to see fine detail infrared for the first time. And so, we have seen a lot of remarkable, phenomena that we had never seen before. And, our models of the early universe are going to be improved dramatically by the Webb because we're getting to see this like we've never seen it before. So that aspect of the Webb is also very, very exciting. And you see a lot of this in social media because the Webb is NASA's first major mission to be done in the epoch of social media. And so, a lot of Webb stuff comes out continuously. Now, some of the social media stuff is, inaccurate, but there's a lot out there that is accurate from good sources. And so we are able to bring humanity along on the journey of discovery via social media. And it's kind of exciting and great from an outreach perspective.
Right, but what are some of the new phenomena that let's get some details if you can.
Well, we've seen a type of black hole that was theoretically predicted to occur before the Webb mission flew, but a type of black hole that results from the direct collapse of gas clouds in the early universe. It is a more massive type of black hole than we've been familiar with to date. We've seen black holes that produce giant outflow jets that are astoundingly large, comparable in size to the voids in the cosmic web, bigger than the galaxy. And, there's a lot of new phenomena like that is waiting to be explained. With the fine detail that Webb can see, we see familiar objects like we've never seen. Supernova, we pick out the progenitor stars and see the detailed structure of supernova remnants like the supernova 1987A that occurred most recently in the solar neighborhood. We can see that progenitor star. We've seen all kinds of, episodic mass ejection from young stars. It's almost all the Webb data is really, really fascinating stuff. We are able to see new stars, that process for star formation that I described with collapsing clouds. We're able to see that process occurring in clouds around us. We're able to see the new stars breaking up the cloud that gave birth to them in a very detailed way. It's really, really, really been wonderful. And I know that you've probably, and some of your listeners have probably seen lots and lots of Webb data online. It's really remarkable stuff.
So what about you said now we could see in high definition, infrared wise, some of the early universe. So what are some features that are coming out that weren't observed before?
Yeah, I wish I could show you pictures. We have seen lots of shock fronts and detailed structure that is completely new to us. Our most recent infrared mission that is now over, the most recent one before the Webb was a mission called Spitzer. And its primary mirror was less than 1 mirror, about 8 centimeters. And of course, the Webb is 6.5. And the telescope's ability to see fine detail is determined by the size of its mirror, 1 over the size of the. And so with the Webb being, more than, 7 times greater in diameter than Spitzer, all the things all the fuzzy blobs in Spitzer data are suddenly into focus as with the Webb data in such that you can see the detailed structure for the first time. So, it's quite remarkable.
Again, anything in particular that, through your own observation, you were surprised about? Any questions that were answered for you from your own observation?
Geez, I'm not actually observing with the Webb, so I don't have a personal project that's happening right now.
Like, I've seen some of the images and some of the comparisons, but to my untrained eye, it's like, oh wow, there's a lot more matter there. There's a lot more, stars and gas clouds, and they color code them so I can see some are maybe methane, some are whatever it is, hydrogen. So that's some of the stuff I noticed. But again, I don't have a trained eye. Like, I believe the pillars of creation, wherever that lies, there was a James Webb image of it, and it looked even more beautiful than before. But I don't know the scientific consequence of what I'm seeing. So I was just wondering, in some of the imagery that you've seen, if anything jumped out at you.
I guess I wish we could have a photograph in front of us. But one of the things that remarkable about the Webb data compared to, say, the Hubble Space Telescope data is that these clouds of gas in interstellar space that produce stars and so forth, the gas is mixed with lots and lots of dust. And so the dust makes the clouds opaque to visible light. So you can't look into the cloud deeply and see the star formation occurring in the optical light that Hubble can see. At the longer wavelength infrared light, that longer wavelength infrared light can actually see through the dust. And so in that pillars of creation side-by-side comparison that I'm imagining you're referring to, one of the things that it shows is that the Webb data can actually see through the dust in those pillars of creation to see the new stars forming that the Hubble data can only infer. And that capability of infrared light to penetrate the dust, pervades all of Webb's data. And so we're not just seeing it in more detail, we can see into previously obscured regions to understand what's happening there.
Okay. Are there certain areas that both the Webb and the Hubble should look at? Is it, the Webb, as I understand it, it's not just a replacement for Hubble, but it's like another lens, literally and figuratively, to see things that you wouldn't normally see with the Hubble. So should both be used in observations or just one?
They are both used in all the time. The way to think about this, the job of the modern astronomer, extract physics information, starlight, to understand the source. So everything we know about the universe outside the Earth, all that information comes to us in starlight. So in order to get all the information, we astronomers want all the light, but all the light doesn't reach the surface of the Earth. The light comes in a spectrum of wavelengths, short to infinitely long. Our eyes are only sensitive to a very narrow slice of that spectrum that happens to match a transmission window in the Earth's atmosphere. So the visible spectrum, as we call it, the familiar colors of the rainbow, that light reaches the surface, and our eyes have evolved to be sensitive to that. But there's a lot more light had, and in order to get that light and the information it contains, that's why we put telescopes in space. And the different portions of the spectrum contain different information. So the info that we can get from visible light is different info than we get from infrared light or radio light or ultraviolet light and so forth. So we have to use these different facilities that are designed to observe different portions of the spectrum. We have to use them together to put together a complete picture, typically, of what we're observing. And so that's very much what NASA's Great Observatory program, of which Hubble is a part, is designed to do, to provide several concurrent facilities that access different portions of the spectrum at the same time.
If I could magically go bloop and put another telescope into space, what range should it look in? Like, what would be like a dream for astronomers? An X-ray telescope, infrared, ultraviolet. What else is needed up there?
Well, it depends who you talk to, but NASA's plan, the successor to the next big thing to be developed after the Webb telescope will be something called the Habitable Worlds Observer. And that telescope was recommended by the National Science Foundation. It is NASA's future plan. It will launch sometime in the late 2030s, and it will be an optical telescope. So it will cover the part of the spectrum that Hubble is covering. Hubble won't last to that point, and that will be the true successor of Hubble. It will replace Hubble with something the size of JWST. And it will be very, very powerful, and it is optimized specifically to observe habitable worlds, habitable exoplanets.
Interesting. What range will it see in the next?
It's in planning now, but it will be the same, very similar to Hubble. UV, optical, maybe a little bit in there.
What would be, could you even have an X-ray telescope? Could you have the other ranges?
You could have whatever you want, but as scientists, our desires exceed our wants.